Hi, everybody. Welcome back to workshop number 3 in the Worldcoin Educate Series. Today we have a different session. We have a duo session with 2 talks. The first one is on ZKML, and the second one is on MPC Uniqueness Checks. So we're going to start off with Modulus Labs with Daniel and Ryan.
Alrighty. Thank you, Rebecca. Hi, everybody. It's good to be with all of y'all. So Ryan and I are the co-founders of a little company called Modulus Labs, and we had the great pleasure working with the Worldcoin team on some new features, new upgrades to the protocol, and in particular on the privacy side. I'll do like a quick, maybe 10-minute crash course, high level, and then Ryan will whiteboard out kind of some of the fun details for us to sink our teeth into, proverbially. Yeah. Yeah. Excellent. All right. Well, as you can see, the title of the presentation is ZKML Hands Off My Eyeballs, which is a little bit intense, but hopefully, it captures your attention, at least here in San Francisco. It's really early in the morning. So uh, with that said, the subtitle maybe more appropriately is how we're going to try to make WorldCoin actually one of the world's most privacy preserving identity services, which would be very cool. Awesome. Okay, so this very quick crash course, high level, is organized around problems. Here are all the problems. We got privacy, trust, ZK, and of course, Ryan and I and our personal problems. But we're going to start with the privacy stuff. And I think what we're going to do is save questions maybe to the end, in part because I can't see your chat. But Ryan, if there's anything really urgent or pressing, you're just going to let me know.
Yeah, I'm on it.
Awesome. Okay. I'm very sophisticated, so I have some really cool graphics and some really cool animations ready for you. So stick with me through this. On one side, you have the user, that's us, and our eyeballs, specifically the data concerning our iris images, right? So those are the raw images of our iris, very sensitive. That's why it's in red. On the other side, I have a building representing a server or a massive computer, and a little robot here, which represents an algorithm. So, in very brief, this is actually meant to kind of depict the current flow or the current strategy for how WorldCoin basically verifies a new user, right? That you are a unique human and that there's no duplicates in the existing database. Very straightforward. The orb takes an image of your eyes. It does some analysis. It then sends that iris code to the server, where an algorithm verifies that everything looks good. You are a unique human. This iris code doesn't match any of the existing entries in the database. Everyone's happy, except not everybody's happy, right? And I'm just gonna skip straight to kind of what y'all already know, which is the problem with this situation. There's headlines about this. TLDR, folks are understandably very sensitive about biometric information, in particular iris data. The government, users in general, even WorldCoin doesn't really want to hold this information, right? It's very sensitive again. And we want to find a way to basically reduce maximally the footprint of these biometric kind of pieces of information uh, within the kind of WorldCoin corpus, right? This is both obviously for privacy reasons. Privacy is a good, but also from a compliance standpoint, as well as just the virtues of kind of decentralization and like having a robust service that is, defensible against bad actors. So let's talk about solutions. This is kind of maybe a little bit obvious to a lot of you, but maybe a first step we can take is basically to just have the data, the biometric information stay with the user, right? So, in the parlance of the industry we occupy, it's called self-custody. So the user holds onto the data, say in their mobile phone, right? So that raw image of your iris or the iris code doesn't get transmitted to a centralized server somewhere. That would be an awesome start. Okay, so that's the first problem solved. We just fixed privacy. Congrats to all of us. High fives all around. We keep the data with the user. The problem that this or gives rise to, however, is around trust. And we're going to get to exactly how in just one moment. All right, so now the data is with the user. The algorithm, the verifying servers, they're on the other side. And what we're actually going to do, the problem with this is that, of course, the user who self-hosts the data can do the analysis maybe on their local device and just send the result. Hey, WorldCoin, I've checked that my iris code, that raw image gives me the right results. You can take my word for it. I'm a unique human, right? And the problem with this situation, again, super obvious, is that when you do this, you open yourself up to these like incredible attack vectors where the user can, now that they host their own data and they have their hands on the algorithm, they can craft pretty sophisticated and sometimes not even that sophisticated attacks. So in this case, you can actually see this is something that's created by one of the folks on our team. We're kind of adversarially trying to attack the WorldCoin algorithm to basically generate unique identities based off of the same raw iris image by just perturbing the image in very specific ways. This took Ben probably like less than an hour. Right? And suddenly we break the whole simple promise of the Worldcoin protocol, which is pretty devastating. So that's a problem as well. Yeah. Okay, so the solution to that problem is hopefully relatively obvious if you've been in the space anyways. It's ZK snarks. Basically, we are going to protect that computation, right? The analysis of the raw image, even though it's happening on an untrusted device, such as the user's mobile phone, right? So we're going to get into exactly how that works in just one moment. All right, third problem, ZK versus AI. So in part because I can't see y'all's faces, I'm not sure what the general background of the folks here is. I'm not super confident how well folks know zero-knowledge cryptography, which is ZKPs. But the good news is that I think DC Builder from Worldcoin Foundation actually has a specific section about ZKPs later in the series. So for the sake of our work on ZKML, we're just going to give you the, again, super high level. And then we can leave the protein for DC next week, I think. Okay, so to radically simplify, all that a zero knowledge proof basically says is that a specific computation happened and it got a specific result. Which I know sounds probably not very convincing, but we can add a little more kind of specificity to it, right? So especially in our case, this particular AI model, right? In this case, the iris code algorithm, inference or kind of made a determination without tampering, meaning without any manipulation from the user or from an attacker, and resulted in this specific output, right? So in other words, it's a promise that a very specific process took place without outside influence. Cool. And this is really key. This is especially relevant to the zero knowledge aspect. Basically, you don't actually have to learn anything about the input data on the verifier side, right? So the server doesn't actually learn a ton about the input image, the iris image, despite the fact that it's now convinced to a really high degree of confidence that the process by which the iris code was derived did not have any manipulation. Awesome. Cool. So just to mush it together one last time, all those small complications, zero knowledge machine learning, ZKML, on the edge in this case being the user's mobile devices, means that a particular algorithm was run over the iris image and resulted in a particular iris code. And most importantly, all while guaranteeing that there was no manipulation by the end user and without leaking the user's raw iris image, right? Their sensitive biometrics. So that is the, in, I guess, a sentence and a half, promise that ZKML is hoping to make on behalf of the user. Cool. So just to go through again, your raw iris image never gets transmitted over a network of any kind. The algorithm which analyzes that raw iris image now comes to your phone, and we prove in ZK this entire process on the user's device to basically guarantee to the the service providing authority, Worldcoin in this case, that in fact the user has not attacked this pipeline, and that they are hopefully a unique human that's worthy of the Worldcoin protocol, right? So winners all around, right? This is a win, obviously, for user data privacy. It's a win for continuing to ensure a really high degree of integrity for Worldcoin in terms of authenticating the identity. And finally, it's great UX in that hopefully this whole process is invisible to the user. It's just happening in the background somewhere. And everyone gets better security while maintaining privacy. All right. One last thing to kind of add here before we dive into the protein. Daniel and Ryan versus AI. Here's Daniel and Ryan. We're folks building this stuff along with the rest of our team, of course. What's our problem, of course? with this whole situation. This sounds wonderful. Why is it that there's an issue here? Well, it basically comes down to um, kind of the traditional setting for running zero knowledge cryptography, right? Which is you get a really powerful computer which generate these like very sophisticated zero knowledge proofs, and then you can send it somewhere to be verified very easily. Uh, as you may have noticed in the very sophisticated pictorial diagram, in this case, the device which is generating the sophisticated zero knowledge proof are oftentimes 32-bit Android phones in developing economies, right? So not big, chunky, powerful AWS server, which is tricky because ZK is, again, a very expensive computational process, right? So the kind of TLD here, DR here is that we need a step change improvement in ZK performance to actually be able to provide ZKML, at scale. So really, really quickly, just to put some numbers to it, kind of the generic, overhead that you can expect, right? So if you wanted to prove any AI kind of result using some of the ZK software that's out there in the open source world, the overhead you should expect is probably on the order of 100, 300,000x, right? So let's say that it takes 1 second for us to prove that, or to derive your iris code from that raw iris image on your phone. Well, it's going to take 300,000 seconds approximately to prove that operation. I don't know how much time y'all have on your hands, but 300,000 seconds is too many seconds, probably. Despite that, we can already build kind of some prototype things at this range, which is some of the things we've done in the past. And you can, go to Modulus Labs .xyz and you can check those out. The good news is by specializing, which is what we do, right? ZK specifically for AI operations like the iris code algorithm, this specialization helps us go a lot faster, right? So these numbers are actually outdated. We're even faster than this by now, right? So that 1 second iris code algorithm now takes maybe 180 seconds. And again, we're even faster than that now. And that starts to bring us into the regime where actually we can do this Worldcoin iris code upgrade on the user's device. And, that would be, again, that win-win-win we mentioned before. So here are some of the specs that, we're targeting for this very specific iris code proving, library that we're working on. It needs to be less than 5 megabytes. It has to have less than, 30 seconds of proving time. And turns out this is the most important bottleneck. We can go no further than 1 gigabyte of peak memory consumption. So if you look at the installed base of the World app, a lot of these devices, top out maybe at 1.5 gigabytes of memory, some of them 2. So that gives us basically the footprint that we actually have to run this, again, very intensive proving process. So that we can, again, still reach as many users as possible and get them that really good data privacy and get them that really good UX. So are we there yet? We're almost there yet. And I think we'll have a lot more to say on this very soon. But maybe just to, again, illustrate the whole point here, by specializing ZK, right? It's like the bullet train versus a school bus, right? Train only runs on a track. It goes in one of 2 directions. While a train is much more flexible, while a bus is much more flexible. But in our case, the train remainder, the name of our proving system, is a lot more efficient. And that's how we think we're going to be able to deliver ZKML on millions of mobile devices all around the world. Okay, that was a whiz-fast crash course in the high-level motivation of this very complicated project. We have simplified some things, maybe to the point of absolute inaccuracy. But the hope here is to give you a general sense of intuition around exactly how we're thinking about tackling this problem, why it's worth tackling in the first place, and why we think it's going to be part of the portfolio of advancements, which makes Worldcoin Protocol one of the most privacy-preserving identity services on the planet. Cool. Okay, that's the start. I don't know, Ryan. Does that make sense to you? Is anything I just said new information to you? And if not, would you be willing to help us sink our teeth into some protein?
No. I think that was pretty awesome. I actually wish I'd seen some of these slides beforehand. That was good.
So look, I worked really hard on those animations. And
Oh,
to be fair to you,
yes.
I also hadn't seen those slides until very recently. But
That's
um,
so fair.
we're doing good. We're doing good. You got it.
Yeah, yeah. No, that's fair. I guess I did want to ask the chat slash the audience real quick. I guess before we get to the whiteboarding slash iPadding session, what questions do y'all have for, I guess, Daniel slash like for us, based on the stuff that you just heard? As in this background context is going to be extremely important. It's very important to kind of conceptually understand like why basically this project is happening. So okay, I'm gonna take some time for questions. Okay, let's see. So Ignaivu asked us on your guidance. Oh, I see. Um, so currently at the moment, I don't think we have too many external opportunities. I think we're working very hard on basically the prover technology internally. And yeah, but well, I think we have uh plans to basically in the future like open source and do some educational stuff. Yeah, but nothing concrete right now. And then I guess Daniel, do you want to look at the other questions?
Of course. I'm unfortunately gonna skip y'all's names because I'm not as worldly as I might appear. I'll just say your initials. So DA asks, what could happen in the future if fake iris data becomes available and is used in AI systems? Great question. So synthetic iris data is a concern because under the current construction of the WorldCoin protocol, all that the service is basically checking is that the iris image, which has been scanned, basically has no existing match in their database, right? So it's not a very satisfying, maybe cryptographic answer, but the pragmatic answer is the orb itself. And I think there's been a hardware session where there will be checks for a lot of other things to try to make sure that it's a real living human being in front of it. You know, temperature, the consistency between the eyes. They're trying to get age verification with the local operator, with the orb, things like that. So not a very cryptographic solution, but maybe a very functional one. Ryan, do you want to take two?
Absolutely. So if World ID were to be hacked and implemented into robots in the future, what solutions could address this issue? I see. Okay, okay. Please correct me if I'm wrong, but it sounds like the idea is that effectively you could have like AI agents or robots that are able to receive world IDs. So I think the whole point of the orb and all of the kind of sophisticated, I guess like stuff that they have on the orb. So I think they have like liveness detection, for example. They even test against like various, I think like animals, if I'm not mistaken. Make sure that people aren't putting like their cats up, for example. Also they scan both of your eyeballs and they do the match, I'm pretty sure, so that you can't, for example, do your left eye with your friend's right eye, with your friend's left eye, with your right eye, with your like that way you can't do all those like different permutations. Like it's got to be like one, right? And so I think basically it all relies on the hardware, as in like as long as the hardware is trusted, as Daniel was saying, then everything is good, right? Then the system can't break. But I think definitely if there were an attack vector where you could issue world IDs basically with authentication, biometric authentication to robots, yeah, that'd be pretty bad. Like, uh, yeah, definitely would be pretty bad to address that from within the protocol. Um,
Or maybe let's do two more questions, rapid
yeah,
round. But just to wrap up with DA, this is a good question on three. How does your knowledge proof work compared to proof of ownership? Um, I guess we would say that they're complementary, right? Proof of ownership is like maybe it's a feature, right? Like, oh, I want to prove that um, I guess, either I own some asset or maybe like I have a US passport or I'm of a certain age. But maybe those attributes that you want to show are kind of sensitive, right? In particular, in terms of their association with your identity. Maybe you don't want to prove that you specifically are 22 years old or 33. You just want to show that you're over 18. There's kind of like an information abstraction layer that is most friendly to both privacy, your personal privacy, and still maximally expressive for the services you want to access. So zero knowledge proofs are basically a bundle of techniques that hopefully can get you that right level of abstraction, right? Convincing the person who needs convincing that you are of age, that you own a specific asset, that you're from a specific nation, but without actually showing your passport image or showing your ID information or showing your like on-chain address, things like that. So we think of them as complementary technologies or features and technologies. And I think Worldcoin ought to be one of the most one of the largest projects that's actively advancing this form of kind of like privacy tech. Yeah.
Yeah. Okay. And then, yeah, we can just try and speed around these. So, D asks, what if the phone doesn't have the capability to deal with the iris data? That's a really good question. TLDR, probably the user will have to go back to an orb basically, to perform basically an upgrade. And then Paul asks, when ZK snarks get more efficient and can be run on phones, what does that mean? No orb required. So there is an orb. The orb is always required, as in the orb needs to be there to take the picture. And people can verify themselves in the sense that, for example, if you want to recompute the iris code algorithm in the case of an upgrade, then you can do that directly on your phone without having to go back to an orb. So that is kind of like the superpower of like keeping basically the data on your phone while still proving that you're running the correct process. Um, cool. And then, so I think R asks about anisocoria and unequal people. I think we're not qualified to answer that, but I think Tangi, who's doing a biometric session later, might be better qualified to answer this. And then what are the organs aspects of humans? Yeah, this is also a Tangi question from you. We definitely do not claim to know anything about biometrics or biometric identification. But thank y'all for the questions, and yeah, please save those for Tangi. Um, Okay, cool. So, with that being said, let's dive into maybe a couple of the maybe just like interesting sort of little challenges that we've run into, as well as a quick, basically just transition into especially the secret sharing, and why the whole secret sharing slash MPC stuff is sort of like necessary.
And thank you, Riddick.
Okay, cool. So let's just talk about basically the basic setup real quick. So, as Daniel kind of showed in the slides, there is going to be the orb. And in this case, I'm just going to draw the orb as this little eyeball looking thing. There is the Worldcoin protocol, which I'm going to draw as basically this big beefy server, to be decentralized, obviously. But at least for now, let's assume that it's just kind of running on a server somewhere. And then finally, there is the user's mobile device, which I'm going to denote by this. So in this process, basically when a user signs up for, I guess, a world ID, there is an initial basically assemblage of data. So in other words, you take a photo of your iris, I guess, and in this case, I'm going to call that iris image X. So X is something which is produced by the orb, and X is going to be sent directly to your mobile device. So in the case of privacy preserving, obviously we don't want to send your iris to the servers, right? And so Worldcoin chooses instead to just send to your mobile device. However, the orb obviously can also do computation. So it's also going to compute what I'm going to call Y2. And Y2 is going to equal something called X of F2, or sorry, F2 of X. And the idea here is that F2 is basically what we call the iris code V2 algorithm. So in other words, this is the second iteration of basically the iris code algorithm. And the result of Y2 is basically this binary looking diagram. So Y2, in other words, looks like basically an image with all ones and zeros. And this is kind of your unique sort of quote unquote hash for your iris code. So in particular, Y2 is going to be the thing which gets sent to the servers, while X is going to be the thing which gets sent to the mobile. Okay. So this is what happens in the kind of initial quote unquote sign up process. And obviously this is a much simplified version. Obviously there's a ton of other things happening, registration, so on and so forth. But this is kind of what's happening with the biometrics. So now let's say that we have a new iris code algorithm. And this is exactly kind of like the one of the key use cases for ZKML here. But let's say that suddenly Worldcoin's biometrics team comes up with an F3. So in other words, there's a new algorithm on the block. And in particular, instead of having Y2 stored here, so Y2 is currently stored on the servers, we instead want Y2 to be X'd out, and we instead want Y3, the new iris code, where Y3 is calculated via basically F3 of X where F3 is basically a new iris code algorithm. Okay, so if we want to do this, how are we going to do it? Well, I mean, the obvious thing, right, since the user is the only person that actually has access to their biometrics, is to say, as Daniel was showing in the slides, hey, user, please compute Y3, right? Please do this computation, Y3 equals F3 of X, and then please go ahead and send Y3 to basically the Worldcoin servers. Now, okay, so obviously I've written this in red, which means that we don't trust Y3, right? Because clearly the user could mess up either the algorithm or the input, as in they're under no obligation currently to either run the correct algorithm, i.e. to have F3 be the actual iris code v3, or to have the input data to that basically algorithm be the correct input data as was given by the org. So these are two pretty fundamental issues, right? If the user is able to send any iris code that they want, well, suddenly the whole system is broken. Every time the iris code algorithm gets updated, you can effectively create a new world. So obviously we don't want this. And we're going to have to find ways to kind of like constrain the user to only do the right thing. What questions do y'all have so far? Sorry, I know this is a lot of notation. No, wait a couple of seconds. Oh, whoops. I just realized I'm sharing my whole screen. Dan, are there any questions I should address?
Not that I've seen. I mean, everyone's riveted, Ryan. Keep going. You got.
Oh, okay. That's good. Okay, cool. So as Daniel was saying, and this is exactly just kind of like a review from the slides, the first thing that we're going to do is we're going to force the user to provide basically a proof. So we're going to force the user to give basically a pi2, and this is what I'm going to call the ZKML proof. And basically, given pi2 as well as what I'm going to call box X, which is a commitment to X. So in other words, a commitment to X basically says, here is something. It's not going to reveal anything about the data inside. However, I can use it to verify that the basically operation that I computed on X was computed on the thing that is inside the box. So,
Real fast, Ryan, there's a really good question from Paul here
mm,
about the directionality of things. So Paul's question here is, sending Y2 to the servers means Worldcoin can reverse engineer our X question mark?
Okay. That is an extremely, extremely good question. And actually, that is precisely the segue into the secret sharing plus MPC stuff. But we might hold that question for now, if that's okay. As in, that is literally the instinct that I think spawned this entire kind of like process for secret sharing and MPC. Okay, cool. So with that being said, the TLDR is that the user sends over now a ZKML proof as well as a commitment to the input of this basically processor function. And so when the server receives Y3 Pi2, oh, sorry, this should be Pi3, my bad. So when the server receives Y3, Pi3, and X, basically it will just verify that Pi3 is correct with respect to this commitment. And now the picture is going to look like the following. Now the picture looks like Y3 equals, and there's a reason that I'm putting that in red, equals F3 of X. So after verifying the ZKML proof, effectively what we know now is that the computation was done correctly. So F3 is now in green. However, there's still one more problem, which is that even though the orb sent over X, which was the user's actual iris image, unfortunately, we have no way to verify currently that the X that the user put here, or the X that the user put in the box, basically, is that X that came from the orb. And so this is bad because now you can basically just take a picture of, for example, your friend's eyeball and say, oh yeah, this is definitely my eyeball. Let me basically compute the V3 iris code of this and send this to the servers. So obviously we don't want this. And that is where part two of kind of like this whole challenge comes in, which is how do you authenticate the input, right? Like, what do you do? I guess actually, can folks type in chat any ideas they might have for this? I'll give it a sec. Also, I can't see the chat, so yeah, I'm gonna need your help again.
I think folks are thinking right now, but in the meantime, Brian,
Mm,
I think the videos are recorded. I'm seeing a lot of like live recording flashing
mm,
iconography.
okay,
So,
cool.
I do think they will be available later.
Okay.
Um, A asks, can you repeat the question?
Yes. So currently, basically with the ZKML proof Pi3, we know that the computation F3 was being done correctly. However, we don't know that the input that the user fed, which is basically this X thing, is indeed the actual iris image, which was basically taken by the orb. As in, the user could have put any iris image that they want to, or just any image, frankly, that they want to there. So the question is, how can we kind of get rid of this problem?
Folks are thinking.
Probably give it like 15 more seconds.
The reason this is a problem is basically, we are asking the users to self custody, right? So they're holding on to their own raw iris images. In the future, whenever WorldCoin updates the algorithm, users right now would need to go back to an orb and redo the whole process, right? What we'd like for that upgrade to look like is for it to be invisible for the users, right? So they have the data on their phone already for them to just run the algorithm again, the new algorithm rather, and send the iris code and kind of update the iris code. The issue is that if the user is allowed to basically intercept that process, let's say they run the app in an emulator, right? And they change the data file that the app references to grab that raw iris image for a slightly different iris image or an attacked iris image, they can now generate a new identity on the WorldCoin protocol. So that's it's existential. In fact, it breaks the entire promise of the service. Um, but Ryan, uh, I wonder if maybe did the orb sign something in the beginning? Can we maybe use that? Oh,
Mm,
wait. Just kidding. K says X
mm.
can be signed by the orb and can be sent to the user. And A says they should have some key to some sort of inverse algorithm, which is computationally hard for someone who doesn't have the key that only the user knows and not everybody. Yeah,
Yep, that's it. Wow.
right. Yeah.
Yeah. Hey, you must be a cryptographer because yeah, that's exactly it. Yeah, absolutely. Okay, so just to recap then, effectively, as A was saying, we need a basically guarantee of authenticity, right, from X itself, or rather from the orb itself. And so not only should the orb send the original iris code, which is Y2, over to the servers, it should also send sign of X comma SK, where SK is the secret key of the orb. Um, and once it sends this signature over to the servers, the second thing that basically the servers are going to do when the user sends over basically this commitment. Sorry, I'm actually going to make one small correction. The orb is not going to send over a sign of X SK. It's going to send over a sign of box S SK, because the server merely needs to basically verify that the commitment to X was computed correctly. And again, all this box stuff is just there for privacy reasons, right? As in, like, the box X does need to be sent to the servers so that the ZKML proof can be verified. But in particular, we need to sign that thing as opposed to X. So, just to recap, all the server is going to do is it's going to basically call verify sign on the box X that the user is sending over, the signature from earlier. So I'm going to call this sign X. And then finally, the PK, where this is the public key of the orb. So, yeah. So for folks who are, I guess, less familiar with like signature schemes, the TLDR is that in these like asymmetric key, quote unquote, signature schemes, users have, or rather, individual parties have a secret key that they can use to sign or to basically create a digital signature. You can almost think of it as like a handwritten signature in some sense, on a piece of data. And then your associated public key, which is something that everyone else knows, is something which can be used to always verify signature if and only if it came from you. And the nice part about signatures, as A was saying, is that they're very hard to forge. So in other words, if, for example, I have my Ryan secret key and Daniel does not have the Ryan secret key, it is very, very difficult for Daniel to basically forge a signature without my secret key, such that my public key would actually verify. Okay, So lots of jargon, lot of words. TLDR is that basically after we verify the signature, now we know that X actually came from the orb. So in other words, this process now looks like, and finally, Y3 can be green. So Y3 indeed equals, and in this case, F3, which was verified by the ZKML proof of X, where X had its signature verified basically via the orb sending over the signature earlier. Okay, so this is kind of like the whole process currently of basically how the iris code is generated. And in fact, the reason that this was kind of interesting in the first place, I think, is because if we look at what happened here, it meant that we had to basically load code on the orb that would literally create this cryptographic commitment to the iris image X and then would sign it. And then also to basically create code to verify the signature later. Okay, pretty cool stuff. So this is kind of like the part one TLDR. And then I guess very, very quickly, or very quickly, what questions do folks have?
So, Chess C asks, in regards to data custody, why is it that when a user doesn't enable data custody, their iris codes get deleted once we have an update to the orb? And I think if I'm understanding you correctly, the reason is actually relatively straightforward. It's basically this attack vector where, you can imagine as soon as the orb updates, right? So presumably the orb is being updated with like a new algorithm to translate that raw image into an iris code. Suddenly all these raw images that previously used a prior version of the iris code algorithm would give you a different result than what the new algorithm would give you, right? And so you have this like you have this like consolidation issue, right? Where you have to like match old iris codes to the new iris codes that the same images would generate. It's basically a massive version control issue. And you throw in there the issue where the user, if they have data custody, so they're holding on to their images, can now potentially mutate that image, right? And literally create a new identity. So the whole point of having ZK here, the whole point of having the orb sign that image initially, which the servers now check against the upgrade process happening on the user's end device, is to make sure that all the versions line up, you don't get duplicate identities. And, as an upgrade going forward, this just isn't a problem anymore, right? It's all invisible, abstracted away from the user. The whole thing just works the way it's supposed to with zero compromises to privacy. So it's a really good question. It's very nuanced. But it's also, again, existential, right? Does the service work or not? It's very binary. Yeah.
Okay, cool. In interest of time, I might just do the last thing very, very quickly. Okay, so earlier, someone in chat, I forget your name, I'm so sorry, but had basically this very, very key insight, which is that, hey, Y2 equals F2 of X. In other words, the orb is computing that initial iris code basically from the iris, right? And then we're sending this currently, at least based on this diagram, in the clear to the Worldcoin servers. Sure, it's binary, but can't someone kind of like invert and say, well, okay, why don't we just compute X equals question mark F2 inverse of Y2? So luckily, this is not quite possible, as in there are many, 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 many different iris images that can actually correspond to very similar iris codes. And so it's not quite possible to directly invert this function. However, it is true that Y2 leaks quite a bit of data about your iris code. And when it comes to biometrics, obviously, we want to leak truly as little information, if not none, as possible. And so basically, there will be a new setup in which there's still the orb and there's still the user's mobile device. But now, rather than having a single server, there are now 3 or more servers, all of which are kind of connected to each other, and each of which are operated by basically independent parties. And so now, the orb, of course, is still going to take the iris image X, and it's still going to take Y2, which equals F2 of X. However, instead of just directly sending Y2 to everyone, instead it's going to create what we call secret shares of Y2. So in other words, it's going to generate Y21, Y22, and Y23 such that in the simplest case, and this is not literally what happens, but in the simplest case, you have that Y21 plus Y22 plus Y23 equals Y2. So in other words, if and only if the parties all collaborate and get together and kind of merge all their shares, can you recover the original thing. So the way it's going to work is that Y21 goes to one server, Y22 goes to another server, and then Y23 goes to the last server. Technically, the way that this is actually done is using something called Shamir secret sharing. I'm sure Lucas can talk about this a lot more. But the very, very short TLDR is that you have some, you basically generate some random polynomial. So I'm going to call it P of X, such that P of Y, P of 0 rather, for example, equals Y2. So the secret is hidden in kind of like the quote unquote like Y-intercept or the root of the technically that wouldn't be the root, but it's hidden in its valuation at 0, so the constant term of the polynomial. And then P at 1 equals, for example, Y21, so the first share. P at 2 equals Y22, and then P at 3 equals Y23. And so the idea is that if P is a degree 2 polynomial in this case, then you can use these 3 shares to basically interpolate the original polynomial and therefore to derive what the 0 or what the constant term of the polynomial should be. So that is the TLDR behind like what is quote unquote actually going on. Also, there's some like ring stuff that's happening, but again, this is definitely out of the scope of here. But yeah, basically Y21, Y22, and Y23 independently on their own do not reveal any information about Y2 whatsoever. And that is because they are effectively randomly generated. It is only when you put all 3 together can you recompose the original thing. And in fact, you actually want to do computations in this quote unquote secret share space to only compute all of the Hamming distances between the share or between the iris code which is coming in and all the iris codes which are located in the quote unquote like databases which are here. Also, the databases themselves are secret shared. Okay, so long story short, when it comes to what needs to happen on the mobile phone, yes, now we have X, and now we can also compute Y3 equals F3 of X. And importantly, we also need the phone to generate the same kind of secret shares of Y3. So from Y3, we need to derive Y31, Y32, and Y33. And importantly, send each of these as well. Sorry, this diagram is getting very messy, but TLDR, we also send these to each of the servers. And so each of these processes is also going to require basically a ZK proof that happens so that we show that basically the user is sending over the correctly generated secret shares. But again, this is just kind of the segue into the actual kind of like secret share / MPC process. I will stop screen sharing and see if there are any final questions. Okay. Sorry, the last part was a little rushed. Cool.
So thank you for that really, really interesting talk. If you guys are interested in this stuff, there is another ZK cryptography workshop coming up by DC Builder. I think next week, possibly the week after. So do come along for that because there's another hour for this to go into this, because obviously it's not something you can cover in 45 minutes. But anyway, thank you, Ryan and Daniel, for joining us for part 1 of this ZKML and MPC workshop.
Also, thank you, Daniel and Ryan, for the perfect segue into secret sharing and MPC. I hope you can now all see the presentation. And yeah, this is the very dry title of MPC Uniqueness Check. But in the other words, if you watched the talk before, it maybe should have the title as the first talk was Hands Off My Eyeballs. This talk should be called Hands Off My Iris Code. As in the end of the last session, we were hinted like the iris code doesn't really let you reverse engineer your iris image, but it still leaks some information in what we want to get rid of it. And before we diving into directly the part that Ryan left with the secret sharing, I just want to give you a short reminder where we are at the Worldcoin tech tree. And even before that, who are we? So we are TACEO, and I'm a co-founder of TACEO, and we focus on MPC encrypted compute for the Web3. Now to the Worldcoin tech tree. So last week we had DC Builder on this Encode Education Series, where we talked also about the overview about the tech tree. And now let's zoom in where we are with this talk. So we are at the ID verification stage, and specifically at the uniqueness service. So where we want to verify, is this iris code a new unique unit? And we had a similar picture drawn by Ryan before. So let's shortly walk through before we dig into the details of MPC and secret sharing. So we have this orb, and we already saw that the orb checks the liveness, that makes the iris image, and does a signed version of the image and returns it to the user. And then the ZKML magic happens on the device, on the mobile device. We saw that before. And in addition to this magic to transforming the iris code or the iris image to this iris code with a zero knowledge proof attached, this also have to prove that the secret shares, so the three parts that we saw before, are computed correctly. And then once this is done, they will be shared with three different parties. Here they are named MPC party 1, 2, and 3. And the actual check if this iris code is unique then happens on encrypted data, so no information leakage about the new iris code and also about all the iris codes that are already in the system, because they are also secret shared between those three parties. And this computation happens cryptographically secure, which is the field of multi-party computation, which is a similar subfield than
Can I
zero
just
knowledge.
interrupt you, Lucas?
Yeah,
I
sure.
think we can still see slide 1. Are we supposed to?
Yeah,
Is that?
you should see slide 3.
I think you might be sharing the PowerPoint window instead of the actual slide.
Okay, let me just reshare. Thanks for the heads up. Let's just share the whole screen, then it's easier. Maybe let's do it just like here. Here it works. Can you see
Yeah.
now slide 3?
Yeah, we can see slide 3.
So let's do a short recap of slide 2, where we see where this is located in the Worldcoin tech tree. I just highlighted that it is here at the World ID verification, specifically at the Uniqueness Service. If you want to get an idea about the more broader tech tree, I recommend you to watch last week's episode from DC Builder. And on the third slide, we have a similar setup like Ryan draw at the end of this session, where you have the orb, and the orb generates this image, checks for liveness, gets your signed image to the user. And then here, the user device, the whole ZKML magic happens, which means transforming this iris image to an iris code and also producing the proof that you computed on the right algorithm, on the right data, and then also producing the right secret shares. So splitting up this iris code into information that do not leak any bit of information. This then can safely be distributed to these three independent MPC parties, which will take care about storing the iris codes in a secret shared fashion so that they do not learn any bit of information about these iris codes. But still, with the magic of MPC, which is a similar subfield than ZK in cryptography, you're able to compute the necessary check, which technically is a Hamming distance check of the new iris code to each of the iris codes that are already in the database, by performing an interactive protocol between these three parties. Once this is done and you get a go, the result is back to the user, and the user can then now submit it to the Ethereum ecosystem for a sequencer, and then you will get the World ID in the end. Now, we have seen Ryan a bit motivating how secret sharing works and why it is secure. he did it with polynomials. I tried to do a bit more graphic. So it's not Shamir secret sharing, although we use it in our protocol. We also use something which is called additive secret sharing. And it's a bit, I guess, more intuitive how it works if you're not having a very strong math background. Then this very simple case, or let's back up. If you want to compute something, it was shown that very early on that this is enough to compute a function if you have additions and multiplications. If you can arbitrarily stick them together, you can compute any program that is out there or in new programs. Now, so if we manage to do these two building blocks, multiplication and addition, we know that we can do any program. So that's why we focus on these very simple primitives. And here, as an example, we want to add two numbers, 33 and 13, in a secret shared way. So how does this work? Let's take the first number, 33. And you break it, as hinted also with the polynomials, up into three different parts. So you randomly choose three numbers with the one condition that if you add them up, they should again be equal to 30. And I think you can already imagine that this doesn't leak any information. If you will receive a 10, you cannot guess what the original number was, like 34. But if you combine all those secret shares, it is still the old original number. Now, in this case, it's exactly what happens on the user device. This happens locally client-side. This iris code that gets produced by the ZKML code is then secret shared into three pieces, where each one is randomly, but together, if you add them, they result in the original iris code. Now, exactly as in this image, the secret shares are transmitted to the MPC parties. That's what's here called distributing the secret shares. So each party receives one share. And the next step, let's do the same with the number 13 here down there. And each party receive also a share of this number. Now, what do they have to do, these three parties, if they want to compute the addition of these two numbers? And because it's an additive secret sharing scheme, they can just literally add those two secret shares that they received, each locally on their own. And here is important to note that those numbers that result here, this intermediary results like 18, 13, and 15, do not leak any information about the final result. But if they got combined together, like with the user at the user's device, it results in 46, which is obviously the right number. So for secret share, for doing additions, it is very elegant scheme. Here we see at the end, the result gets shared to the user, so the user can assemble the numbers again. Now, maybe it's even that easy if you're doing multiplication, so computing on secret shares, but now the multiplication, like something like 34 times 13, which is, if you even just approximately, definitely above 300. And if it would do it naively, like we did it with the addition, you would get 45 for the first party. You would get 40 for the second party because the shares 8 times 5 and 50 for the third party. And now let's add those numbers together and it would result in 135, which is obviously wrong. So for the case of multiplication, it is more difficult and involved to do this in this distributed setting on secret shares. What you have to do here is now an interactive protocol, and this is what we call the MPC protocols. And Ryan was already mentioning there are two very canonical MPC schemes that we're using, like Shamir secret sharing and additive secret sharing. If you're more familiar with ZK, you can maybe think a bit of it like different proof systems that you can leverage for doing some certain tasks. Now, the theory about multi-party computation is as old as CK, so it's in the 1980s. But also, as we have seen from Daniel, the overhead sometimes is very large. And let's look at the problem, or at least the performance target that we want to have. In the case of the first talk, we had the very restriction and the issue that we had to do everything on the mobile device. Here we don't have to do the stuff on the mobile device except the secret sharing, which is very cheap. But what we have to do, we have to compute on the whole database. So currently, I think about 6 million users. So it's even without privacy, it's quite a huge task. And the goal for the performance was at the beginning of the project that we achieve like 10 to 20 verifications per second, which just literally means that 10 to 20 people each second on the world can go visit a orb and get verified. And for just one verification, we need over 300 million iris code comparisons. So just checking this Hamming distance to an existing iris code. Why is this number so huge? It's like, because we have 6 million humans already in the database, we have 2 eyes and there are 31 rotations you have to check. So for the details why this is necessary, I think the TLDR here is just, otherwise it wouldn't be secure if we wouldn't do this 2 ISOs and 31 rotations. But the best way is to tune into the biometric session. I think that we go into very detail here why you have to design the system in this way to make it secure. Now, at the beginning, we started where the literature, so academic papers, and academic papers could do like 2K iris codes per second. And this is really, I made it in bold because you can just do less than 1 verification per day. So we're so far away of our goal. It's like we've seen with this 300,000x overhead of CK virtual machines. We're so far away that we might even not think about even starting this test. But we did. And our first prototype using techniques inspired from machine learning, so multi-party computation machine learning, got us to 50 verifications per day, which is still far, far away from anything practical. We know we had some room with optimizations. And so we started switching between different MPC protocols on the fly. So this can be maybe imagined like in the first talk, you had designated proof systems for machine learning. Now we had designated MPC protocols for this iris check and a lot of low-level engineering optimization, which brought us to 200 verifications per day. So like 4x improvement, still far away what our target is, like over 10 verifications per second. And again, machine learning, or at least the ideas of machine learning, saved the day here. So we explored this area, which was heavily under-researched, like graphic cards and NPC. And like writing the code dedicated for the GPU and an extremely powerful hardware setup now allows us to do 13 verifications per second. So just above the threshold we want to have that everything is running smoothly and a lot of users can be onboarded to work. Now, for those curious, this setup is each MPC node consists of 8 H100. So this very powerful graphic cards that mostly used for AI training. 6 million users sounds a lot, but the goal of Worldcoin is way more ambitious. And for growing to 1 billion users, this solution won't scale because the performance of this solution scales only linear in the number of humans. So if the database grows, this gives a lot of overhead. So we cannot simply, even without MPC, so without privacy, we cannot do a linear scan search so easily for 1 billion users. So we have to do something like sublinear scan search, which is if you're familiar maybe with vector databases, it goes in just this direction. But with MPC, it's again very underexplored because extremely hard that you do not leak information if you're using approaches like from vector databases. So this is the current ongoing research where the Worldcoin team, TACEO, and several other companies are trying to push the boundaries in applied research here. So this was a very quick walkthrough about the MPC uniqueness check. If you're going to go into any more detail, I would recommend you to use the blog, for example, from the Worldcoin Foundation, where there's also some nice animations and some longer video explanations. And if you're already quite familiar with MPC, you should check out the paper that we have written together with the Worldcoin Foundation, which is publicly available. It's called The Large Scale MPC. You can find it on ePrint and download it. But yeah, here it is really necessary to have some background in cryptography and MPC.
Thank you very much, Lucas. We've actually got, I think, 7 questions from Brian. He's listed them for us. So
Okay,
are you able to see the chat, or do you want me to read them out to you?
I can now see the chat.
Okay.
It's
It's
okay.
from 6:20. Oh, I don't know what time it is. About 10 minutes ago. There's a lot.
Yeah. So if you rescan your iris at the orb, will this result in duplicated iris data? Again, I think this is more of the biometrics talk, but I guess the whole purpose of the project is that it doesn't result in duplicated iris data. So you want to have uniqueness, otherwise you would break the uniqueness property. Exactly. Proof of membership. How could you proof of membership help advance the work for users with the world layer? I think this is maybe best explained by DC Builder, how the proof of membership helps the Worldcoin community. I guess you can read a lot about the homepage there, how you can leverage the World ID now, and also about ideas how it can be leveraged in the future.
Thank you very much, Lucas, for that mini workshop alongside Daniel and Ryan earlier. I'm sure everyone has really enjoyed this 2-in-1 on a Monday. Coming up on Wednesday is the biometrics talk, so lots of your questions can be asked then as well, and I'm sure you'll learn. You'll have some of your questions answered before you've had the chance to answer them anyway. Ask them rather anyway. Other than that, unless anyone has some MPC related questions for Lucas, we'll end the session there for today. Brian has atted me, but
I can also share my Twitter handle in case anybody wants to reach out afterwards.
that would be great. And I'll leave the link to the book that you put in the chat in the video recording, which, by the way, is on the Encode Club YouTube channel from tomorrow for everyone who's asked. Okay, so we'll end it there for today then. Thank you very much, everyone, for joining us. Lots of thanks in the chat. Any guided research projects possibly as well? Agnivo's asking, do you know anything about research projects in the Worldcoin ecosystem, Lucas? I'm not sure. This probably isn't your field of.
There's this grant program. So there was a wave 0 and wave 1 where a lot of great research have happened. I think you can read it in the Worldcoin page, and yeah, reach out to DC Build also, who is a major force in the grants program there.
Yep, that is true. And DC Builder is running the last 3 workshops of the series, so you can have a chance to ask your questions to him then. Okay. Thank you very much. I will see everyone on Wednesday for the biometrics talk. Thank you for joining us, everyone.